In our lecture, we discussed the important technique of Principal Component Analysis, or PCA, for reducing the dimensionality of the data. This technique is especially useful in today's big data environment, where datasets may come with hundreds or even thousands predictor variables that are sometimes highly correlated or redundant. PCA can effectively reduce the number of variables to a more manageable size and at the same time removes any redundancy between the variables. So in this demonstration, I'm going to show you how to perform PCA in R using a dataset that contains the country-level health and population measures for 38 countries from World Bank's 2000 Health, Nutrition, and Population Statistics database. This technique works equally well on both small and large datasets. Now let's first go to RStudio. We're going to import the health data into a data frame or table and label the new data frame as My Data, as we always do. The health dataset can be found in the Chapter 8 dataset file. So we use the Import Dataset tool in RStudio, import it from the Excel data file, and browse to the Chapter 8 dataset. And select the Chapter 8 datasets Excel file. And I'm going to select the health dataset. And rename this data frame to My Data. Click on Import to import the data frame. Now we have imported the data frame into RStudio. Okay. Now let's start a new R script. Go to File, New File, and R script. Now that the dataset has been imported, let's take a look at the first few observations in the data frame using the head function. Let's run this script. Alright, the result shows the first few observations of the data frame. As you can see, the dataset includes the country names and the following 12 numeric variables: the death rate per 1,000 people, health expenditure per capita, life expectancy at birth, male adult mortality rate per 1,000 male adults, female adult mortality rate per 1,000 female adults, annual population growth, female population, male population, total population, size of labor force, birth per woman, and birth rate per 1,000 people. So one glance of the data would reveal that many of these numeric variables are probably highly correlated. For example, the values of the male and the female population would likely correlate highly with the total population and the size of the labor force. And intuitively, we would expect that the mortality rate be negatively correlated with health expenditure in this dataset. So this suggests that there is opportunity for dimension reduction to remove information redundancy in this dataset. As dimension reduction techniques such as PCA are usually performed on predictor variables and numeric variables. In this dataset, we assume all the variables are predictor variables, and all variables except the country name are numeric. We will first remove the country name field so that it is not included in the analysis. Also, as we discussed in the lecture, PCA results can be distorted by the scale used to measure the variables. So in order to resolve this issue, we will standardize the values of the variables by converting them into the unitless z-scores. We can accomplish both of these two things by using the following statement. I'm creating a new data frame called mydata.st, which stands for standardized, and use the scale function to convert the mydata data frame and remove the first field, which contains the country name. So as you can see, this statement first removes the first column, which is the country name, from the data, and then uses the scale function to convert the remaining variables into z-scores. So converting data into z-scores is a necessary step in most PCA applications, as the variables are likely measured using different scales. For example, we use percentage for mortality rate, and we use millions for population, and etc. This step can be skipped if all variables are measured using the same scale as in cases of answers to a survey that uses the same 5-point or 7-point Likert scales for all the questions. The resulting dataset is stored in a new data frame named mydata.st. Alright, let's run this line of script. If you want to take a look at the transformed dataset, we can again use the head function to look at the first few records of the mydata.st data frame. As you can see, now all the values for all the variables have been converted into z-scores, which is unitless. Now to perform the principal component analysis, we use the principal component function in R. The only required parameter for this function is the dataset that contains the data, and preferably the standardized data. The function assumes that the first row of data contains the variable names, and we will perform PCA on our dataset by entering this command. Now let's run this line of code. So this command performs PCA and would store the results in an object called PCA. To view the results, we use the summary function. Now let's run this script and take a look at the result. Now let's take a look at the result from the PCA function. The first section of the result shows the importance of components. As we discussed in PCA, the first principal component, or PC1, would account for the most variance in the data, and the second principal component, or PC2, accounts for the second most variance, and so on. The table shows that in our case, the first principal component accounts for 46.62% of the total variance, and the PC2 accounts for 24.7% of the total variance. And cumulatively, both PC1 and PC2 would account for 71.31% of the total variance of the data. If you look at the first four components, together they would account for over 90% of the total variance in the data, suggesting that by retaining only the first four principal components and ignoring the rest of the principal components, we are going to retain over 90% of the total information in the data. This suggests that the dimensionality of the data can be significantly reduced by converting the original variables into principal components. Now, as we discussed in the lecture, principal components are simply weighted linear combinations of the original variables. So to view the weights assigned to each variable, we can look at the rotation attribute of the PCA object by typing in this command. Alright, now let's run this command and take a look at the result. The result here displays the weights associated with each variable to compute the values for each principal component. For example, the weight for death rate for PC1 is 0.1261, and the weight for healthcare expenditure for PC1 is negative 0.2780. While the weights tend to show the relative importance of each variable in creating the principal components, we usually do not read too much into these weights in most cases. However, it is still interesting and useful to know where the principal component scores came from. So in addition to the number of principal components that should be used to retain a large portion of the information in the data, we are also interested in the final principal component scores that would replace the original values in subsequent analysis. So to view the principal component scores, we can look at the X attribute of the PCA object by using this command. Now let's run it and take a look at the result. The result shows the final principal component scores. As you can see, the PC1 score for record 1 is negative 0.0966, and the PC2 score for record 1 is 0.4045, and so on. Now that we have these principal component scores, we can choose to use the first few principal components to represent our data set in subsequent analysis, because they account for a very large portion of the information in the data. For example, if I'm going to run a cluster analysis on the data set, instead of using all 12 original variables, I can perform the cluster analysis on only the first 4 principal components instead, because this would allow me to retain 90% of the information in the original data. And another advantage of doing this is that the principal components are all uncorrelated with each other, so it would remove any chance of multi-collinearity problem in my analysis. Now, to prepare the data for subsequent analysis, we can paste the principal component scores into our original data set that has the country names. Let's do that. I'm going to create a new data frame called new data. And use the data.frame function to combine my original data frame, my data, and the principal component scores. Let's run it. So this creates a new data frame that contains all the original data and the principal component scores. If you take a look at the first few records of this new data frame, you will see that the data frame contains all the original data as well as the principal component scores of the dataset. Since we are no longer going to use the original data for subsequent analysis, I'm going to remove the original values from this new data frame. And I'm going to remove column number 2 to column number 13 of this new data frame. And then let's run it and take a look at the new data frame. So as you can see, the resulting data frame only contains the country names as the first column and then the principal component scores as the rest of the columns. So this is how to perform PCA in R. As you can see, PCA allows us to significantly reduce the dimensionality of the data by replacing a large number of original variables with a few uncorrelated principal components that retain a very large portion of the information in the dataset. However, these advantages come at a price, as principal components are simply the weighted linear combinations of the original variables. They are abstract and cannot be easily interpreted, and this may present a challenge to the analyst if the interpretation of the results is important in subsequent analysis.